Hello, in this video we're going to look at the variance of the sample variance, or derive the variance of the sample variance. Some of this I'm going to assume you already know, and the formula for the sample variance is this, divided by n minus 1. It can also be rewritten as this, which ends up being a U statistic, but we're not covering that. And this derivation was my previous video, so if you Google statistics math, interesting formula for sample variance, then this derivation is there. It is an unbiased estimator for the population variance. A couple notes about the variance: if we add a constant, the same constant to every data point, it doesn't affect the variance. And also like a shortcut formula for the variance is the expected value of x squared minus expected value of x squared. So we're going to look at V, which is the sample variance with a constant added to it, or subtracted. So the variance of V and the variance of S squared are going to be the same. The expected value of V is 0. Okay, so now let's start in. The variance of S is same as the variance of S squared, plus a constant. So that's the variance of V, and the shortcut formula says the variance of V squared minus the variance of V quantity squared, where we just showed that the expectation of V is 0, so this is 0. So it's just equal to the expected value of V squared, which says S squared minus sigma squared squared. So then that can be rewritten as this. Now we're going to replace what S is in each of those. There's S and this is S. Now there are choose 2 of these elements, the summation. So if we multiply by it and subtract or divide by it, then we get the same denominator there. So it can actually be taken into this sum, same way over here, and that's what we do next. So now this is the sum of that, because this is a constant, so there'll be choose 2 of them. So then it eliminates by the denominator, so we get that back. So it is true. And then so then, since this is the product of sums, we can rewrite it as, we can take this sum over here and rewrite it. So just algebra so far. Then we can take the expectation into the sum, because it's a linear operator. So we have the expected value of this. Now we're going to take, since this is a product, we're going to take, this times this. And my daughter would call it the FOIL method. I think that's pretty common now. So we take this times that, this, that, and we get this expression. So now there's different cases we have to consider. Also, there's going to be a star, because in a page we're going to come back to this spot. But for now, we need to stop and break it up into smaller pieces. And we're going to consider 4 cases where none of these indices are the same, where I and K are equal and J and K, you can see it, and then I and K equal not, and then I, K not, and these 2 equal. So let's look at case number 1. So all of them are equal. So I and K are equal, and J and L are equal. So that's actually to the 4th power. And then that is this, and then you can K and an L. I mean, they're all different. Oh, I'm sorry, I said that backwards. They're all different, and we have to keep them separate, like this. Now, since the X's are independent random samples, we can break that into the expected value of this times the expected value of that. So that's going to be sigma to the 4th. And then this is sigma squared, so that's minus sigma to the fourth, so those two cancel. And then this will cancel. I mean, this is sigma squared, so minus sigma to the fourth plus sigma to the fourth. Anyway, that's 0. So whenever they're all not equal, we can ignore it. Okay, so now let's look at the second case where I and K are the same and J and L are the same. So that's this case. And then so that first part here is just, since they're the same, we can raise it to the fourth power. And then these will be just the same. So this whole thing is sigma to the fourth, so which cancels with that. And then this is sigma to the fourth, so we get this. And then if we bring out the fourth in front, and then add a u and subtract a u, now we're going to FOIL this to the fourth, or use the binomial theorem or Pascal's triangle or whatever you want to call it. And when we multiply this out, we get this big dog. And then don't forget the minus sigma to the fourth, and there's a 1/4 out front. So now when we take the expected value into this, then we're just going to call that the fourth central moment, the mean. Here, since I and J are independent, that's the product, but this is 0, so that goes away. This here, they're independent, so that's going to be sigma squared, sigma to the fourth. Here, they're independent. That expectation is 0, so it goes away. And this is just going to be mu 4, which is this. Then minus that, and then this reduces to this. Now, we're in the I equal K and J equal L scenario. So if we need to know how many, so this ends up being a constant, but we need to know the constant to multiply it. So I and K equal and J and L equal. So if we randomly choose I and J, there's n choose 2 of them, but once these are picked, then those are fixed. So there's n choose 2 ways to have I equal K and J equal L. And that's what I put down here. There's n 2 ways to choose I and J, but once those are picked, then there's only one way to pick K and L, because they have to equal. So there's a total of n choose 2 times this. Okay, so now let's go to situation 3, where I and K are equal, but J and L are not. And then we get this. And notice that I put an I in there for the K. And I did the same thing here. So now when we, with this piece here, this will be sigma the fourth, cancels with that. And here we're just left with a minus sigma the fourth, which is this. Then we, what we're going to do is add and subtract mu in here and add and subtract mu in here, and that's what we get here. Now let's FOIL this and FOIL that. So we get this square, that is this foiled, and then this is that foiled. Now we need to FOIL this and this. But I'm going to not do it and just kind of walk you through what I do. So this foiled with this is this piece here. Okay. Now this foiled with this, the I's will combine, here and here will combine to be a third, but then this is by itself. So when they're independent, so you take the expectation, that goes to 0. We're not going to include it. Now this foiled with that is this. So this foiled here, all of them will go away because this is 0. And then here we get I and, oh, it won't. Oh yeah, well, because this is an L, which is independent. So that when this multiplied by this expectation, that'll make it go to 0. This with that, then the L's will combine, but that's still left by itself, so that goes to 0. So then this piece is right here, that times that, and then expected value. This times this, they're independent, and this is 0, so it goes away. That times that is this. So now minus fourth comes down. So then this is just the mu 4 over 4. And then this is going to be sigma squared times sigma squared, sigma fourth over 4. Same way here, same way here. And then we have the minus out front. Then this can be combined into this. Okay. So now we need to know how many ways that this constant will be added together. So if we look at our original sum, and I and k are equal, but j and l are not. So if we randomly pick these, there's choose 2 ways here, then k has to be I, so there's one way to pick it, and this one has to be different than them all. And then so once we pick this and this, there's only n minus 2 ways left over. So there's this. So the n minus 1 over 2, that's the n choose 2. And then there's n minus 2 ways to choose the L. So we're going to take this constant times this. So then there's one more case, and that is when j and k are equal and these are not. And it's so similar to case 3 that I'm gonna hand wave, and we end up getting the same constant, and it's the same number of ways. So we're on the last page here. So here's our asterisk, so we're coming back to this. So then we fill in the knowledge that we just gained. So this was out front, and then so we have, this is case number 2, this is case number 3, this is case number 3. So this is identical to that, so we can combine them. So it's 2 times one of those, so the 2's cancel. And then so this reduces to this with, and then that multiplied in. So then this multiplied in gives us this, and that multiplied in gives us this. Okay. Now, we start adding, or combining like terms. So here we factor out a mu 4 minus mu squared. Oh, actually, in this step, I didn't combine them. In this step, I combine them. So that comes down. Then we get everything over a like denominator. We get this. And then it reduces to this. And then we get that. And that's the final answer. And this is what you see in books too. Now, one reason that I'm doing this is the next video, we're going to look at how to use projection to determine normality or asymptotic normality. So if you have a statistic that is not independent, the sum of independent random variables, you can't use the central limit theorem. And so what you do is you project that onto the sum of independent random variables. You project it onto that space, and then the projected image you show as normality, and then you end up showing that the difference of the original statistic and the projection are so close that you conclude that it's also normal. This is what's used in a lot of non-parametric statistics, and this is how they prove that U statistics are asymptotically normal. Anyway, that's going to be the next video, but I wanted to show this first. Thanks, hope you enjoyed it. If you did, please like it, subscribe so you don't miss the next one. Thanks, bye.